We've looked at alkanes in linear and branch conformations, and actually alkanes and some alkenes as well can exist in cyclic or ring forms. So let's take a look at cyclohexane. And one of the differences between hexane and cyclohexane is there are two less hydrogens. So when we look at the formula for hexane, C6H14, there are 2 times as many hydrogens plus 2, whereas in cyclohexane, there are just twice as many hydrogens as there are carbons. And that's going to be true for any cycloalkane. And here we see the line structure for cyclohexane, which is a hexagon. Now, cyclohexane is a fairly common ring structure of an alkane, and one of the reasons is when it is in its ring structure, the carbon-carbon bonds can get really close to 109.5. For example, if we look at cyclopropane, which only has 3 carbons, it's really hard for them to get 109.5 when they're sort of in a triangle shape. So getting back to cyclohexane, it has 2 conformations. It has what's known as the chair conformation, where if we look down here at the bottom of this slide, we see sort of how the carbons are at each angle here of this graphic would be a carbon. And then there's also the boat conformation. The chair conformation is the more stable conformation because there's less interaction between hydrogens. So according to the Vesper theory, it would make sense that cyclohexane spends most of its time in the chair form. Now, this is an important geometry because glucose or blood sugar also forms a 6-member ring in the bloodstream, and it also tends to take on this chair rather than the boat conformation.